Hey folks, let's talk about some of the other types of chemical sediment besides carbonate that form that 5% of all sedimentary rocks that we talked about earlier. We'll start with evaporite sediment. Evaporite sediment consists of minerals that precipitate from an aqueous solution when those minerals are concentrated in the solution due to the evaporation of the water. As water is removed from a lake or sea by evaporation, the remaining water becomes saturated with respect to minerals like calcite, gypsum, and halite. These minerals precipitate in the water column. They can precipitate at the sediment surface underneath the water. They can precipitate at the water surface where evaporation concentrates things the most and then sink to the bottom. And they can also precipitate within a saturated column of sediment, in other words in the subsurface, from pore water. This photograph here shows what are called efflorescent crusts of halite that are forming because water from the subsurface that's saturated with respect to halite is being drawn up from the subsurface by the intense evaporation in the dry air of Death Valley. As that air draws salt-saturated moisture out of the subsurface along these mud cracks, the water evaporates and the salt is left behind, and it crystallizes out as sort of a mound. And that term again is efflorescence. These are efflorescent crusts, and the term efflorescence means basically to flower out. So the salt is flowering out of the subsurface. Okay, as you evaporate a freshwater lake, the salts that it contains become more and more concentrated in the remaining liquid. So if you start with a freshwater lake and you evaporate the water, you will turn that freshwater lake containing low salt concentrations into a saline lake. And any lake, if it's left in a situation where evaporation exceeds the addition of new fresh water to the lake, will evolve in this way over time to a saline lake, and if evaporation continues to shrink the lake, it'll eventually evolve to a very dense, heavy brine. And a brine is a supersaturated aqueous solution containing lots of salts. As salts become more and more concentrated in a brine, the water becomes more and more difficult to evaporate, but it becomes a lot easier to precipitate minerals from it. Really dense, bitter-tasting bitterns are hyperconcentrated brines, and these pools shown in this image are hyperconcentrated from lake water that used to fill the entire valley here, and once that lake evaporated, you ended up with these super concentrated brines or bitterns in brine pools on the surface, and these are where evaporite minerals precipitate really rapidly. The most common evaporite minerals are carbonates like calcite or aragonite, sulfates like gypsum, or chlorides like halite. And what determines which category a given mineral falls into is the anion in the chemical formula. So carbonates all have the carbonate anion in them. Sulfates all have the sulfate anion in them. And chlorides all have chlorine. This list of 9 evaporite minerals includes the most common ones that precipitate from seawater when it evaporates. So when you evaporate seawater, mostly you're going to get calcite, gypsum, and halite. Those are the 3 most common, and those are the 3 that I'm going to continue to talk about the most. However, because lakes have different chemistry than the oceans, the minerals that lakes precipitate can be much different from these. Every lake is different, and depending on the chemistry of a particular lake, they may precipitate completely different sets of minerals. A much wider variety of minerals than just these 9 are precipitated, therefore, from lakes. Many of these minerals have economic value. So the image in this slide here shows gypsum crystals that were precipitating from the bottom of a lake. They basically grew upwards into the water column when this lake was still filled with water. And that would have been a brine at that point. Once these gypsum crystals formed, the lake shrank even further. This part of the lake bed dried out, and now these poor crystals are left stranded away from the brine, their parent brine. And the reason I show this is to make the point that evaporite minerals, just like any other type of sedimentary deposit, can be picked up and reworked by other currents. And in this case, these gypsum crystals are picked up by wind blowing sand across the bottom of this dry lake bed. They break up into sediment. That sediment gets carried downwind and deposited in the sand dunes that make up White Sands National Monument in New Mexico. And those sand dunes are called White Sands because they're entirely made of gypsum. And this is the source of that gypsum. When evaporite minerals precipitate from a shrinking water body, they do so in a particular sequence that corresponds to the solubility products of the minerals involved. Highly soluble minerals like halite, which dissolve really readily in fresh water and remain in solution, they can remain in solution within a brine until you evaporate approximately 90% of the water. So if you take seawater and you evaporate 90% of it, it's only at that point that you can begin to precipitate halite. You evaporate 50% of seawater and you can begin to precipitate calcite. You evaporate 75% of the water and you can precipitate gypsum. And this is because calcite is less soluble than gypsum, which is less soluble than halite. And then these at the bottom, these bittern salts, are the most soluble of all. So this sequence of minerals is commonly found in evaporite deposits. So let's say that we have a lake as shown at right, and these are all contours, depth contours on the lake. So the deepest part of a lake is right in here. And let's say the shoreline of the lake is out here so that it's a pretty big lake and it's all full with salt water. Let's say seawater. Now let's evaporate 50% of it. When we evaporate 50% of the water in a lake, it's going to shrink, so we get a new shoreline. Our old shoreline is stranded out beyond that new shoreline, and it's in this new lake that's much smaller that we can begin to precipitate carbonate. As we continue to evaporate the lake, we'll shrink it even further. Here's a new shoreline, and underneath this new lake, we can begin to precipitate out sulfate, like gypsum. If we evaporate it even more so that now we're at 90% evaporation, we've shrunk the lake even further, so the new shoreline is here and the lake is much smaller, and it's in this small pool that's remaining where we can deposit chloride minerals like halite. And if we shrink it even further, we might get just isolated brine pools or bittern pools where we can precipitate these other minerals. Now, as a result of this, when you take an ideal lake filled with water that has the chemistry of seawater, approximately, you'll end up precipitating out evaporite minerals in a series of concentric rings or zones. The outermost zone, the carbonate zone, would be where you could precipitate out limestone or calcite. The sulfate zone would be the area where gypsum is found, and the chloride zone would be the area where halite and maybe some of those bitter salts could be found. So a good example of this occurs at the floor of the Mediterranean. So this map here is showing France, Italy. Here's the coastline of Spain. There's the border between Spain and France. And then we're getting up into Italy. So we're just looking at the western portion of the Mediterranean. And then down here is Morocco, Algeria, etc. And these are the islands of Sardinia and Corsica. So that's the outline of the Mediterranean. The Mediterranean is what's called a silled basin. Meaning that it's a sea that is isolated from the open ocean by a barrier or a sill. So this would be our sill. This would be our basin. And then out here would be the open ocean. Well, what this means is if sea level were to go down, say during a glaciation, when you lock up a lot of water on the continents, the sea level drop will turn this silled basin into a lake because it's no longer connected to the ocean. And that's precisely what happened to the Mediterranean during a time period known as the Messinian, about 22 million years ago. Sea level dropped, and the Mediterranean basin turned into a lake, and because there were not enough freshwater inputs to that lake to sustain it, it slowly evaporated. And the minerals that precipitated out on the bottom of the Mediterranean follow the sequence we just talked about. The black areas are the carbonate zone. The lighter colored stippled areas are the sulfate zone, and anhydrite is just a dehydrated form of gypsum. And then the halite zone would be in the center here, that big bullseye. So you evaporated 50% of the water to start precipitating carbonates, 75% to start precipitating sulfates, and then 90% to start precipitating halite. And this zonation is pretty good evidence that you evaporated that body of water completely. Now, how thick are these deposits? Well, evaporation of a 1,000-meter deep column of seawater theoretically would produce about 12.5 meters of halite, about 1.7 meters of gypsum, on a flat, even seafloor. So if we had a container like this with 1,000 meters of water in it, we'll get deposits of those thicknesses on the bottom. Now, if the bottom is uneven, like this, then as we draw down the water column, it'll separate out into pools. So the thicknesses of evaporite minerals that you find in these pools might be different than the predicted thicknesses that you'd find on a flat bottom. But still, these numbers are pretty good. This is about what you could expect. You wouldn't expect it to be too much thicker than that. And you'd certainly expect, in any case, that you would get more halite from the evaporation of seawater and less gypsum. However, in a lot of ancient deposits, such as the one photograph on the right here, this is all laminated gypsum. These are, the white are gypsum deposits, and the brown are thin mud deposits, and these have been deposited in annual layers called varves on the floor of an evaporating sea. And these deposits are pretty much entirely gypsum. There's not a lot of halite in them at all, and they're up to 650 meters thick, which is way thicker than we'd expect if we just took a 1,000-meter deep sea and evaporated it entirely. And as a matter of fact, you couldn't just evaporate something once and get anything this thick. The other weird thing is that there's little to no halite in here, and you'd expect that you'd have more halite than gypsum if you evaporated something completely. So why is this? Well, the answer is that evaporites accumulate in what I like to call the evaporite distillery. And this evaporation occurs in association with a complex set of inputs and outputs. And those input and outputs can be modified to a rate that can hold the brine at concentrations to precipitate just one mineral for a really long time. So let's look at this illustration on the bottom here. We have freshwater input, either at the surface or from groundwater, that can go into this brine. We have water being removed by evaporation. We can have water being added through rainfall. We can have inflow of marine water, salt water from the ocean over the surface or seeping through some barrier. And all those water sources combined are what gives the brine its chemistry. That brine can then be held in a particular state so that it precipitates one mineral for a long period of time, or it can continue to evolve into a denser and denser brine, and if you get a brine denser than the underlying pore water, it'll actually seep down into the subsurface. So this evaporite deposit here is controlled by all of these factors. It's not like you just take one lake and evaporate entirely that lake and then you're done. So evaporite precipitation occurs in several places. I talked about this earlier. Evaporite minerals can, so this, let's say this is a brine surface here. So there's our brine surface. We can make evaporite minerals and grow them in several different settings. Evaporite minerals very often will form right at the surface of a brine because that's where evaporation concentrates the salts the most. And once those crystals form and get big enough, they start to sink. They can sink straight to the bottom and accumulate as a deep water deposit, or they can sink down to shallower water where the brine may still be concentrated enough for them to continue to grow. Precipitation, once these minerals fall to the bottom of a brine pool or something like that, let's say we take this part of this situation and just blow it up over here, and let's say we're dropping halite crystals onto the bottom. Those halite crystals will accumulate in a sort of randomly packed pattern, sort of like this, on the bottom of that brine pool. And once they are deposited, they will start to continue to grow upwards from the bottom, and the growth will occur most rapidly along the corners of these because that's where you have the greatest surface area, and so these guys here will tend to grow faster. And eventually, overwhelm the growth of everything else. And so commonly what you get in a halite deposit and a gypsum deposit that has grown from the bottom upwards is you get this pattern of growth. It's called a chevron pattern. That's what it looks like with halite. Gypsum accumulates in crystals like the ones I showed you stranded on that dry lake bottom, where it's pretty clear that they just grew upward from the bottom of a lake. Once the minerals are precipitated, they can be reworked by currents just like any other mineral. So any of these gypsum crystals that precipitate up here can be broken off by waves or currents and deposited in deeper water as turbidites, Balmer sequences, and that can intermingle with gypsum that's falling down from above. Precipitation can also occur in the subsurface. So down beneath the surface of the sediment, you can have brines there as well that will continue to precipitate evaporite minerals, and a lot of times those minerals can grow and displace the sediment around them, and we call that displacive growth. And that displacive growth can actually deform layers of sediment that are already existing. All right, let's talk about dolomite now. Of all the carbonate environments that we talked about last time, they all precipitate either calcite or aragonite with varying proportions of magnesium substituting for calcium and calcite to give us high magnesium calcite or low magnesium calcite. Dolomite is a mineral that contains equal proportions of both calcium and magnesium. So the chemical formula for dolomite is equal proportions calcium and magnesium, and that makes dolomite a really ordered mineral to have those equal proportions. It's the most stable form of carbonate chemical sediment, and dolostone is a really common rock. This whole mountain range here, the Dolomites in North Italy, are made of dolomite. But the formation of dolomite, especially in recent and modern environments, is problematic because dolomite doesn't form as a primary precipitate from the oceans. Hence, we have something called the dolomite problem. So dolomite is not a primary precipitate in modern oceans, although some lakes do precipitate dolomite directly. And it cannot be created in the lab without really high temperatures. So if you heat up calcite and put it in the presence of some magnesium-rich fluids, then you can convert it to dolomite pretty readily. And this is one way that dolomite forms, but it requires pretty deep burial to temperatures of 60 degrees or more to make it happen. However, dolostone and dolomite is common in the sedimentary record. There's a lot of carbonate rocks, about 20%, that are dolostone. The ratio between dolostone and limestone increases with age, so Cenozoic dolostones are a lot less common than Paleozoic dolostones, which are in turn a lot less common than Precambrian dolostones, and this probably just reflects that the older the rock is, the more deeply it's been buried, and that it's been exposed to higher temperatures to make more dolomite. But the real big problem is that we can find very recent sedimentary deposits near the surface of modern sedimentary environments that have been dolomitized. So dolomitization, rocks that were originally made of calcite have been converted to dolomite fairly recently in many carbonate-rich environments. And with a lot of ancient dolostones, we can also infer that those were converted to dolomite fairly readily as well. So let's talk a little bit about why dolomite doesn't form. Dolomite is thermodynamically, at least, the most stable, lowest energy type of carbonate that should form. So dolomite should form because thermodynamically it's favored over other minerals like calcite or aragonite that are less stable. However, in order to make it form, you got to get magnesium into the crystal structure. And we talked about this earlier. Calcium is a pretty big ion, and magnesium, being lower on the periodic table, is a lot smaller. And for that reason, it's smaller and lighter. It's more tightly held to water. It's hydrated. And the calcium ion, being heavier and larger, is less hydrated than magnesium, so calcium ends up bonding with carbonate much quicker than magnesium can, and as a result, dolomite can't form because calcium basically makes calcite faster than dolomite can form at all. So dolomite should form, but it can't. At least not directly from seawater because it takes too long and too much effort to make it. So here's a good illustration of this. This is a paper from 1998, and you're looking just at the title and the abstract. The title is Failure to Precipitate Dolomite at 25 degrees C, that's surface temperature, from dilute solution despite 1,000-fold oversaturation over 32 years. So this person put basically little crystals of calcite or dolomite into a seawater solution and let it sit, constantly running fresh seawater over it for 32 years to see if he could get dolomite to precipitate. He had the solution oversaturated with respect to dolomite, and still it didn't happen. Here's the abstract, which I love. Dolomite failed to precipitate despite more than 1,000-fold oversaturation from dilute solution after 32 years. And after those 32 years, it pretty much gave up. So the problem here is a kinetic problem, meaning it's a rate problem. Calcite forms fast, dolomite forms slow, and therefore you get limestone and calcite rather than dolomite. But there are a few ways that you can make dolomite, and here they are. Dolomite can form if the magnesium to calcium ratio increases and the calcium to carbonate ratio decreases. So basically, if you just increase the concentration of magnesium in seawater, that's going to slow down the incorporation of calcium into carbonate minerals while speeding up the incorporation of magnesium and carbonate. And that's going to tend to favor dolomite, and this is probably the main thing that happens in lakes that are able to precipitate dolomite directly. You can also slow the growth of calcium carbonate and slow everything down by just lowering the salinity of seawater, and that gives ordered dolomite time to form by reducing the overall rate of carbonate precipitation. So basically this would be not necessarily speeding up dolomite so much as slowing down the growth of calcite. At higher pHs, excessively high, the oceans are about 8, you have less bicarbonate and more carbonate, and that would favor the precipitation of dolomite as well, because you got more carbonate ions that need something to bond with. And then lastly, you can heat up the environment. Heating up the environment, heat speeds up any chemical reactions. It's going to dehydrate magnesium and speed up the precipitation of dolomite. So here's a three-dimensional graph showing basically the top 3 of those conditions: the carbonate to calcium ratio, the magnesium to calcium ratio, and the salinity. And this plane here, colored blue, is a plane in 3 dimensions. Above that plane, dolomite will form. So if we increase magnesium calcium, if we increase carbonate to calcium, or if we decrease salinity, we can favor dolomite instead of calcite. Modern day seawater is right there. That is on the calcite side of this plane, but again, if we either increase the carbonate to calcium ratio, increase the magnesium to calcium ratio, or decrease salinity, we can induce dolomite to be the primary phase to form. One of the main models for dolomite precipitation involves flat desert evaporite settings called sabkhas. And this is a photograph of the Abu Dhabi sabkha in Saudi Arabia. These occur in many places, but the type locality is the Arabian side of the Persian Gulf. The basic idea here is that seawater periodically floods the sabkha. So you will get, let's say, a shoreline like this, and you flood it with seawater, and maybe you've got some barrier out here to trap that seawater. And then you evaporate all the water, and you concentrate a brine here. When you concentrate that brine, you'll start to precipitate minerals out of it, like calcite and gypsum. And these will eat up calcium in the brine while leaving magnesium behind. As you precipitate these evaporite minerals, you concentrate this brine, which becomes pretty dense. And once it's denser than any pore water underneath it, it will sink into the subsurface. And, once it sinks into the subsurface, it is a magnesium-rich dolomitizing fluid that can pass through the rocks and sediment in the subsurface and convert the calcite and aragonite into dolomite. And you would need to do this repeatedly. Let's say have a tidal flat that's flooded and then evaporates repeatedly, and those fluids then pass through the subsurface and dolomitize the sediments that are found there. So here's a little bit better illustration than the one I just drew of that same concept. This is called the hypersaline model, or the brine reflux model, or the sabkha model. They're all sort of variants on the same thing. You have a little bit of a rim here, or a sill, that separates this evaporative setting on the left from the open ocean on the right. You flood that periodically. You let this brine evaporate to the point where it becomes more dense than what's underneath, and then this whole area here ends up being inundated by those fluids as they percolate downward. And as they percolate down through the sediment, they react with it to convert it to dolomite. Another model involves decreasing salinity, and this is an appropriate model perhaps in less arid environments, and recent dolomite is known to occur in places like the Bahamas that you wouldn't necessarily consider to be a desert. In this model, you have fresh water, meteoric water, rainwater, that is falling on some landmass above sea level. That water is slightly acidic. It'll percolate down into the subsurface and dissolve caves and things. It'll open up cracks. And it'll accumulate underneath the water table. So we've got fresh water here in this area, the phreatic zone. In other words, the zone where the sediment is saturated with water. But then over here we've got an ocean, and that seawater will percolate down into the subsurface as well. And where those two meet, you get mixing. And if you make seawater a little bit less salty, we would call that a brackish water, and that brackish water zone may move from time to time, but it'll always exist in the place where sea and fresh waters meet in the subsurface, and dolomitization can happen along this zone. The last thing that I'll say about dolomite is that dolomite may be able to form simply by just continuing to react limestone with normal seawater in the subsurface. So you remember Oswald's step rule before. The first phase to form is not necessarily the most stable, but if you continue to leave it in the environment in which it formed and let it continue to react with the fluids that were its parent, it'll eventually convert into something more stable. And so the idea here is that if you have some way to continually flush carbonate sediment with seawater, you can convert that carbonate sediment into dolostone simply by just letting it continue to react with seawater. That'll probably take a lot longer than the schizohaline model or mixing zone model here, and probably take a lot longer than the hypersaline model as well, but that's one way that you could, one additional way that you could create dolomite from limestone. And then finally, the last way to make dolomite from limestone is probably the way that most older dolomites were formed, and that is simply by burying them to higher temperatures where reaction rates will get sped up, and that conversion to dolomite can happen a lot more quickly. Okay, the last chemical sedimentary rock that I'd like to talk about is chert. Chert is a deposit of pure silica. It's quartz. It can form either as a primary deposit of silica from microbes, marine and lake microbes that build silica shells instead of carbonate shells, and they do this near the sea surface. They're photosynthetic. These microscopic critters are called diatoms and radiolaria, and again, they're unique because they build their shells out of silica instead of carbonate. And once they die, their shells, which are called tests, accumulate on the seafloor. They basically sink to the seafloor and accumulate in thin, usually annual layers like the ones shown in this photograph. So this is a photograph of some deformed, banded chert, and each one of these layers is probably an annual deposit of the rain down of all these microscopic shells onto the seafloor. These typically accumulate in cold or deep water beneath the carbonate compensation depth, where you don't have competition here with carbonate deposits. The silica that the organisms use to build their shells gets into seawater either from continental sources, i.e. weathering, which leaches silica from rocks on land and washes it into the oceans, or more commonly due to adding silica to the water from volcanoes on the seafloor. So a lot of times these ribbon cherts, as they're called, accumulate near seafloor spreading centers where there's abundant silica in the seawater. Another way that chert can form is as a replacement product. It can replace limestone or dolostone pretty easily if you just change the chemistry of the pore waters that run through that limestone or dolostone, make them silica rich and more acidic. They'll dissolve away the limestone or dolostone and reprecipitate quartz, or just reprecipitate it by diffusion, basically exchanging silica molecule by molecule for carbonate from the fluid to the rock. So here's an example of some diagenetic chert. These mounds are stromatolites. We talked about those before. So these are those microbial colonies on the seafloor that precipitate calcium carbonate. And the upper surface of them, they are basically draped over by more micrite, carbonate mud, through here. And this dark colored rock in this area is all chert. And that chert has incompletely replaced some of these thinly laminated carbonates that sit above the stromatolites. And that replacement probably happened during fairly deep burial. There's another chert band up here that basically replaced nearly an entire layer of carbonate, or an entire bed. So all of this is chert. And you can kind of tell it's chert from the photograph because it's sticking out further from the outcrop, and that's simply because it's made of quartz, which is more resistant to weathering. So those are the two main ways in which chert forms. Because this is a sedimentary geology class and we're not talking about burial yet, I'll talk mainly about just the first case, how you produce primary chert on the seafloor. So seafloor chert deposits form from the deposition of radiolaria and diatom tests like these. So this image is showing some of the really ornate skeletal structures that these microorganisms can produce. And they're tiny. I mean, like 10 microns tiny. They're really small. They are made not of chert. They're made of hydrated silica, which we call opal. So these are opaline tests of diatoms. They once these organisms all live near the sea surface, so they're living up here, high in the water column, diatoms and radiolarians and some other things. Those siliceous organisms live for a while and then die, and when they die, their tests settle down to the bottom. And if the bottom happens to be either below the CCD or in cold water where there's not a lot of carbonate production near the sea surface, then they can accumulate down at the bottom as a siliceous ooze. The word ooze being pretty evocative of what that is. It's a mushy, muddy mess made up of those opaline tests of the organisms that died, and then the tests sink to the bottom. As those tests get buried, they go through a series of transformations. First, that unlithified ooze is converted to a more crystalline opal A form, one structure of opal. Again, still hydrated silica, but more crystalline than the amorphous silica that those tests are made out of. And then as it's buried deeper, it'll convert into opal CT, which creates a rock type called a porcelainite. So we go from this ooze to something that looks more like a chalk, to something that looks more like a porcelain rock. And then finally, if we bury that even deeper, we can turn all that opal into true quartz, which is what we call chert. And again, the silica that gets in the water in the first place either comes from volcanic input, So submarine volcanoes or hydrothermal vents can pump up silica into the seawater and saturate it with silica, and those environments are great places for these siliceous organisms to thrive. Silica also gets into the ocean from rivers that carry the products of weathering to the oceans in solution. A lot of that stuff will get reabsorbed by clay minerals on the seafloor, but some of it can make it into solution, and these siliceous organisms can then build their shells from it. Okay, well that's it for chemical rocks. Thank you all for listening. We will start talking about sedimentary environments next.